Okay, so a quick revision on transformers. What do we know about transformers? Transformers, they basically transform or transmit electricity over long distances. And if we want to transmit electricity over long distances, it's usually we usually transfer them with very high voltages. How can I increase the voltage? How can I step up the voltage using a step up transformer? So we have two types of transformers. It's either a step up transformer or a step down transformer. Let's draw the basic transformer. Usually it has a not usually, it always has an iron core. This is an iron core. It has to be an iron core. It cannot be steel. It cannot be any other material. Why does it have to be iron? Because iron is a temporary magnet. And then we have coils on either side of the transformer. We have the primary coil, which is the input. Okay, this is called the primary coil. Let's write down the primary coil. Okay, primary coil, which is the input. And then we have a secondary coil. A secondary coil. And if for any reason he asks what is the material of the coil made of, the material of the coil is made of copper. Any wire is usually made of copper. So we have iron and then we have the copper coil. The primary coil and the secondary coil can tell us whether this transformer is a step-up transformer or a step-down transformer. In this case, we have the primary coil with much less turns than the secondary coil. This means that the secondary coil has much more. So I know it's quite obvious. This indicates that this transformer is a step-up transformer, meaning that the voltage will increase. The input voltage is whatever voltage, and then the output voltage on the secondary coil would increase, would be much greater than the input voltage. A step down transformer, so let's write down that this is a step up transformer. A step down transformer would look almost exactly the same, with the only with a slight difference that the secondary coil has less turns. The secondary coil would have less turns, indicating that this is a step down transformer. So I have much fewer turns on the secondary coil, but much more turns on the primary coil. So this is a step down transformer. This is a step down transformer. So basically, we have power input and power output. Power input and power output. For a 100% efficient transformer, the power input would be equal to the power output. How can I calculate the power, or how can I calculate the input voltage or output voltage? We're going to be using two very important equations. The first equation, which is the more commonly used equation, states Vp over Np equals Vs over Ns. Vp, okay, in which Vp is the primary voltage, and Vs is the secondary voltage. Np is the number of turns on the primary coil. Number of turns on the primary. Ns is the number of turns on the secondary coil. Okay, so we have usually you'd have three of them, and he'd be asking you to find the third one, which is quite easy. It's a simple cross multiplication equation. You just cross multiply to find the voltage, the output voltage, the input voltage, whatever is needed, whatever is required. This is the first equation, the more commonly used equation. The second equation is related to the power input and the power output. Power input and the power output. How so? I told you that if you have a 100% efficient transformer, the power input would be equal to the power output. What is the power, or how can I calculate the power? Okay, so we can say power input is equal to the power output, in which power is VI. So VI is equal to VI. Okay, but I can say VP IP is equal to VSIS. VP IP is equal to VSIS, in which IP is quite obvious is the primary current. Primary current. And IS is the secondary current. Okay, but this equation is inversely proportional. This equation is inversely proportional. It's not directly proportional. Directly proportional voltage and the number of coils. As you increase the number of coils, the voltage increases, and vice versa. But in this case, as you increase the voltage, what happens to the current? The current decreases. Current decreases, which is quite beneficial. It's an advantage actually for transmitting voltages, for transmitting power over long distances. It is an advantage to decrease the current, and I'll tell you why in a very short time now. Okay, so now we have two equations that are used in transformers for 100% efficient transformers. What happens if the transformer is not 100% efficient? You can just find the power output and then multiply by the efficiency. If he says it's 70% efficient, okay, then you just multiply by 0.7 and you can find the output current or output voltage or whatever is needed. Okay, that's if the transformer isn't 100% efficient. Okay, we have some questions. Okay, some questions. They're quite rare, but you have them. You have some questions when you're required to find the voltage or the current when the transformer isn't 100% efficient. Okay, how does the transformer actually produce the output voltage? How does it produce the secondary voltage? Sometimes in other questions, why does a transformer use an input current or an input voltage of an input alternating current? Why does the current have to be alternating? Okay, so basically, how does a transformer operate? How does a transformer, okay, how does a transformer operate? You need to state several things. First of all, the input current has to be alternating. Okay, so okay, the alternating current in the primary coil, in the primary coil, creates, okay, generates whatever, creates an alternating magnetic field, an alternating, okay, magnetic field. And this is actually a keyword that you have to say, alternating magnetic field, which keeps on changing. That's the whole point of the transformer, that the magnetic field keeps on changing. It's like a magnet which keeps on moving in a generator. The generator, you have something that keeps on moving. It's either the magnet or the coil or whatever. So there's some motion. In the transformer, there is no physical motion, but there is a magnetic field, okay, or there's a motion or there is a change in the magnetic field. So as the alternating magnetic field, as the magnetic field keeps on changing, what happens? It keeps on cutting the secondary coil. Okay, alternating magnetic field cutting, which is the second keyword, okay, cutting the secondary, okay, cutting the secondary coil, producing an induced EMF and current, producing or generating an induced EMF and current in the secondary coil, okay, in the secondary coil. Okay, so you have some very, very important keywords in this statement. First of all, you need to say an alternating magnetic field is created in the primary coil, which keeps on cutting the secondary coil, and then it produces an induced EMF or an induced current in the secondary coil. Usually, this question is worth 3 to 4 marks. Okay, usually 3 or 4 marks. So you have some keywords in which you have to state them. You have to state these keywords while solving this question. How does a transformer operate? Okay, you have the iron core. Sometimes he might ask you, why does the core have to be iron? Why does the core have to be iron? Sometimes, okay, when you have this question, you can say you can say that the iron core acts as a magnet. Okay, it acts as a temporary magnet which keeps on transmitting this magnetic field. I said it creates a magnetic field. So the alternating current in the primary coil creates a magnetic field, which could be transmitted by this iron core. The iron core keeps on creating a magnetic field which is transmitted through this iron core. Okay, so that's if he asks you why does the why does the core have to be iron. Okay, so this is how a transformer operates. And then, what are some of the advantages of operating, or what are some of the advantages of transmitting power at high voltages? Advantages of transmitting power at high voltages. At high voltages. Why do I need to transmit power at high voltages? As I said, as you increase the voltage, what happens to the current? First of all, you have to say that the current decreases. The current decreases. When the current decreases, what happens? The power lost decreases. Power lost decreases. Power lost decreases. Why? Because you have an equation for the power. Power equals VI, yes, and you have another equation which is power equals I squared times R. You have another equation which is power equals I squared times R. So the current has a very huge factor. Current has a very huge factor. So I squared times R, P equals I squared times R. Also, as you decrease the power lost, the energy lost decreases. Energy lost decreases. So you might say, okay, you might say it's a bit more efficient. You can also use thinner wires. You can also use thinner wires, which is economical, more economical because you don't have to pay that much to buy very thick wires. Okay, it's more economical using thinner wires. So these are some of the advantages of transmitting power at high voltages. So basically, this is all we need to know about transformers. We don't have that many details. Okay, and transformers is a very, very easy session. Honestly, it's one of the more easier sessions that we have in physics. Okay, we have a step up, step down transformer. Basically, we need to transmit power over long distances. We have two equations, and that's it. How does a transformer operate? And that's all you need to know about transformers. Can we start solving some questions regarding the transformers? Yes, definitely we can start solving some questions. So let's open up our classified questions. Okay, this is page 378. Page 378. Okay, page 378. Okay, question 11. You have figure 11.1 that's showing a solenoid connected to a battery. On figure 11.1, draw a pattern of the magnetic field inside and around the solenoid, indicating the direction of the magnetic field with an arrow. Can I indicate, or can I find the north pole and the south pole of this magnet? Yes, I can find the north pole and the south pole of the magnet. How? This is a solenoid and I can find the current, and then I can see, okay, as I told you last time, you need to figure out in which direction is the first part of the coil moving. In which direction is the first, is it above or below the core? For example, we can consider, okay, we can say that we have an iron core. Okay, this is the iron core. Okay, let's see. In which direction is it moving? Is it moving below or above the first part? If you consider, if I go from above, okay, so it's moving kind of above the coil using the right hand rule grip, using the right hand rule grip, you'd find your thumb, it's moving downwards. I know it's a bit difficult to use the right hand rule in this question to find that the thumb is moving downwards. How can I solve it a bit easier? So if the thumb is downwards, this would be the north pole and this would be the south pole. And now I can draw the magnetic field. Can I make it a bit easier? Yes, I can make it a bit easier. Let's just think about if the current was moving in this direction. Okay, don't draw the arrow. If the current was moving in this direction, can I use my right hand rule? Yes, I can use the right hand rule grip. I'd find that the thumb would be pointing upwards. That's if the current was moving in this direction. So if the current was moving in this direction, I'd find that the thumb was pointing upwards, indicating that the North Pole would be above and the South Pole would be below. But this isn't the case. This isn't the case. Actually, it's pointing in the opposite direction, indicating that the North Pole is downwards and the South Pole is upwards. Can I draw the direction of the magnetic field? Yes, definitely I can draw the direction of the magnetic field. It's from the north to the south. So inside the coil, he said you have to draw inside and around the coil, inside and around the coil. Inside the coil, you have to have some straight lines, some straight lines. They have to be straight. And you have to draw the arrows pointing, you have to draw the arrows pointing from north to south. Okay, so it's always moving. Okay, okay, you have some arrows from north to south, and then around the coil, it's moving this way. Around the coil, it's moving from north to south, and then on this side, we have an arrow moving outside from the North Pole, and on this side, you have an arrow moving inside into the South Pole. So this is the direction of the magnetic field around this solenoid. Okay, you need to draw these arrows using your right hand rule grip. Okay, I told you for this question you can just think about whether if the current is moving in the opposite direction, so you'd have your thumb pointing upwards, but for this question it's actually moving the other way around, so the arrow would be pointing downwards. Next question. You have power is transmitted at a voltage of 400 kilovolts. A transformer reduces the voltage to 33 kilovolts for use in heavy industry. The number of turns on the primary coil is 11,000 turns. Can I find the number of turns on the secondary coil? Can I find the number of turns on the This is a step down transformer, isn't it? Yes, it is a step down transformer. So you have VP over MP equals Vs over Ns. The input voltage, the primary voltage is 400 kilovolts. Can I just leave it as it is 400? Yes. Why? Because the output or the secondary voltage is 33. So I'll just leave it as it is, because the more zeros I write down, the more the higher the possibility that I could forget a zero while calculating using my calculator. 400 kilovolts, and then the input or the primary coils were 11,000 coils. Can I cross multiply? Yes, I can cross multiply. So basically 11,000 times 33 divided by 400 gives you a 907. So you have 907 turns on the secondary coil. Okay, this is NS. Okay, let's solve a couple more questions. Okay, a transformer has 500 turns on the primary coil and 25 turns on the secondary coil. The input voltage is 120 volts. Can I find the output voltage? Yes. Again, VP over MP equals Vs over Ns. Please, you have to write down the rule. I know that you know it very well, but again, write down the equation. Vp over MP, the input voltage is 120 volts over NP. This is not NS, this is NP. 500, 120 over 500 equals Vs over 25. This is a step down transformer, so 120 times 25 divided by 500 would be 6. Okay, 6 volts. The current in the primary coil is 125 milliamperes. MA is milliamperes. It's 100% efficient. Can I find the output current? Yes, VPIP equals VSIS. VP was 120 times 125 milliamperes. So 125 divided by 1000, which is divided by 1000, which is 0.125, is equal to 6 times IS. 6 times IS. Basically, you need to divide by 6. Just divide by 6. And the current would be 2.5 amperes. 2.5 amperes. Okay, I have a loose wire connected a circuit. The length of the wire between the two supports. Okay, the power supply is switched on and the wire moves down. Draw an arrow to show the direction of the current. Draw an arrow to show the direction of the current. In which direction would this current move? Is this a DC? This is a DC motor. It's quite obvious. You have a DC power supply. You have a DC power supply. So you'll use the Fleming's left-hand rule. Fleming's left-hand rule. Basically, north to the south, which is the index finger, and then the wire is moving downwards, so the thumb is pointing downwards, and therefore your middle finger would point to the left. So current is actually moving in this direction. This is the movement. This is the direction of the current in this wire to the left. The power supply is switched off and the wire returns to its original position. The power supply is then switched on so that the current is in the opposite direction. State and explain what happens to the wire. What happens to the wire if you reverse the direction of the current? If it was initially moving downwards, then it would move upwards. Okay, it would move upwards. Why? Because you have reversed the direction of the current, and therefore you will reverse the direction of the force. It will move upwards. Moves upwards. Okay, it moves upwards. Why? Reversing the current versus the force on the wire. The force on the wire. The wire. A split ring commutator is an important feature of a DC motor. Split suggests one reason why the DC motor cannot operate without a split ring commutator. Without the split ring commutator, what would happen to the motor? Would it keep on rotating? No, it doesn't. So one reason is because the coil would not rotate in a continuous rotation. Okay, the coil will not rotate in continuous motion in the same direction. In the same direction. Okay. Power is produced in a power station by an alternating current. The output of the generator is 22,000. The electrical power is transmitted at 400,000 volts. Explain why electrical power is transmitted at the voltage of 400,000 and not 22,000. Again, as you increase the voltage, what happens to the current? The current decreases. So you can say that the power loss decreases, the heat loss decreases, and we can use thinner wires. Okay, as voltage increases, what happens to the power? First of all, you need to say that the current decreases and then the power lost. Power lost decreases. Since power is equal to I squared times R, you can say that the heat energy lost, okay, that the energy lost also decreases. You can say that you can use, okay, you can use thinner wires. You can use thinner wires. A computer contains a transformer. The input voltage to the transformer is 240 volts. The output voltage from the transformer is 20 volts. And the output current is 2.3 amperes. The efficiency of the transformer is 90%. Calculate the input current to the transformer. Okay, interesting. The efficiency of the transformer is 90%, and we have the output current, which is 2.3 volts, 2.3 amperes. Output voltage is 20, so let's write down. Input voltage, this is VP. Output voltage is Vs. Output current is Is. Can I find IP? Yes, I can find IP. First of all, can I find IP? Yes, you have the current. You have the equation. The equation is VP IP equals VS IS. VP IP equals VS IS. Um, let's calculate it. P equals VS IS. Basically, to find IP, it would be equal to VSIS over VP, which is 20 times 2.3, 20 times 2.3 over 240, which is 20 times 2.3 divided by 240 is 0.19. Okay, let me write it down. 0.1917. Okay, this is the IP, but this is the wrong current. Why is this the wrong current? Because this is not including that it's actually 90% efficient. 90% efficiency for the output voltage and output current means that this should increase. This number should increase. How would it increase if it's 90% efficient? So basically I can divide by 0.9. I can divide by 0.9. So if you divide this number by 0.9, it would give you a current of 0.21. So the actual current, the actual input current is 0.21 amperes, 0.21 amperes. Okay, because it's 90% efficient. Okay. Hmm. Okay, a transformer consists of two coils of wire. State the name of the metal from which the core is made. Definitely, is made of iron or soft iron. Okay. The primary coil of a transformer is connected to the output voltage of an AC generator. Explain why there isn't a voltage between the two terminals of the secondary coil. Again, he's basically asking you how does this transformer operate? How does it operate? Basically, you need to say that the input voltage of the input current is alternating. Alternating current. Alternating current in the primary coil. In the primary coil produces, okay, or creates an alternating, okay, magnetic field. Okay, let me write it down. Magnetic field, which cuts, which cuts the secondary coil. Secondary coil producing producing an alternating induced current. An alternating induced EMF and current. And can I find there are 560 turns on the primary coil, 900 turns on the secondary, the voltage in the secondary, this is Vs and this is Vp. Hmm, This is sorry Np, and this is Ns. Can I find the Vp? Yes, Vp over Np equals Vs over Ns, so we need Vp over Np, which is 560, equals Vs 78 over 910. 78 over 910. Can I cross multiply? Yes, you can cross multiply. Okay, something. Okay, can I cross multiply? Yes, 560 times 78 divided by 910 is 48 volts. Okay, 48 volts. Hmm. Explain why the power losses in the cables are lower when the voltage is high again, because the current has decreased. Okay, current decreases, and when the current decreases, what happens? The power lost decreases. Okay, less energy lost due to the heat. Okay, power equals I squared R. Okay, less power lost. Okay, less energy lost. It's lost as heat energy. If you remember, as the current increases, the heating effect, the wire actually gets hotter. So less energy is lost due to as heat due to heat energy. Okay, lost to the environment. Okay, I guess that's quite enough for transformers today. I know that transformers are quite easy, so we can just solve many more questions regarding the transformers. Not that difficult transformers questions. If we move on to Unit 5 and the atomic physics, okay, Unit 5, atomic physics. It's a very easy unit, honestly. Okay, physics. Okay, it's a quite an interesting piece of cake. Yes, I always say piece of cake. Atomic physics. That what is atomic physics? Basically, half of the atomic physics is talking about chemistry and the structure of an atom and the number of number of neutrons and number of protons, number of electrons. And if you have a neutral atom, then the number of electrons would be equal to the number of protons, which is okay. We know all of that, basically. And one of the more important questions that we have, again, it's a chemistry question. I know. What is an isotope? Okay. So an isotope is an what are isotopes of elements? They have the same number of protons. They have the same number of protons. Okay, protons, but different number of neutrons, or sometimes we can say nucleons. And nucleons is different, is not neutrons. Nucleons, for those of you who do not know what a nucleon is, it is actually the mass number. It's the mass number. So sometimes if he asks you what is the nucleon number of this element, the nucleon number is the mass number. He's not asking about the neutrons, he's asking about the mass number, nucleon. So an isotope is used in atomic physics. Why do we use isotopes? Because basically isotopes create unstable atoms. They create unstable elements. When you increase the number of neutrons in the nucleus, the element becomes unstable. The element becomes too heavy, it becomes unstable. So it basically starts to give off some radiation. It either gives off alpha or beta or gamma. So let's just split the board. Okay, let's zoom in a bit. Okay, so you can have either okay, alpha radiation or beta radiation, okay, or gamma radiation. Alpha, beta, or gamma radiation. What is the difference between them? Okay, let's write them down. The alpha radiation, okay, well, it's not a radiation actually, it's an alpha particle. Alpha particle. How do we write the alpha particle? It's alpha A4 and 2. It's A4 and 2. Basically, it is a helium, and we need to memorize this. It's a helium nucleus. It's not a helium atom, it's a helium nucleus, meaning that it has the same number of protons. It has two protons, okay? It has two protons, two neutrons. The mass number is 4. The mass number is 4, okay? But it has no electrons. Therefore, when I ask you about the charge of the alpha, the charge is positive 2. The charge is positive 2. This is the charge of the alpha, meaning that it's very highly ionizing, okay? It's strongly or highly ionizing. The mass is 4, and therefore it's quite a heavy element. Okay, it's quite a heavy element. So the distance traveled by the alpha is very short. Okay, short distances. Also very slow speeds. Okay, very slow speed. What about the penetration effect? The alpha cannot penetrate. It's very weak. Okay, very weak penetration effect. Very weak penetration effect. Why? Because it's heavy, it's big, it's huge. Okay, cannot penetrate most of the. It can be stopped by a very thin sheet of paper. What about the beta? Quickly, what is a beta element? Beta is it's an electron, 0 and -1. So it's basically an electron produced from the nucleus. It's produced from inside the nucleus. It's not an electron from the shell. You need to understand this. It's not an electron from the shell. It's an electron from inside the nucleus. Okay, that's why we call it a beta. It's not just any electron. What does a beta mean? It means that it has no protons. It has no protons, no neutrons. You kind of might say that the mass is zero, okay? The mass could be zero, or actually, to be more specific, it's 1 over around 2000 or 1 over 1840. It's a very, very small number, okay? Usually we consider it to be zero, okay? It's 1 over 2000. We can say that it's almost zero. The charge of a beta is negative 1. The charge is negative 1, meaning that it's not very high ionizing, not it's medium, okay? So medium ionization, okay? Something in the middle. Medium ionization. It's weaker than the alpha. The ionization effect of the beta is weaker than the alpha. What about the distances traveled? It travels further distances. For the alpha, it can travel a distance of, I guess, up to 5 centimeters. Up to 5 centimeters. Okay, longer distances. Okay, longer distances, I guess, around up to 5 meters. Okay, much longer. The speed is much faster. Okay, faster speed than the alpha. What about the penetration? It has a stronger penetration. It has a stronger penetration. Okay, it can go through it can go through a sheet of paper, but it cannot go through a thick, okay, sheet of aluminum. Thick sheet of aluminum would stop it. What about the gamma? Gamma is basically an electromagnetic radiation. Gamma is an electromagnetic radiation. Electromagnetic radiation, meaning that it has a speed of what? Of 3 times 10 to the power of 8. Speed, okay, is 3 times 10 to the power of 8 meters per second. It has no mass, it has no charge, it has nothing. So zero, you can say it has the weakest ionization effect. Weakest ionization. It's almost non-existent. Okay, weakest ionization. You can say extremely long distances, travels at least 5 to 10 kilometers. Okay, much longer distances. Okay, longest distances, you can say up to 5 kilometers, 5 to 10 kilometers. Definitely the speed, as you said, 3 times the speed of light, 3 times 10 to the power of 8 meters per second. What about the penetration? It's the strongest penetration. Okay, strongest penetration. It can go through the paper, it can go through aluminum, it can be weakened or kind of absorbed by a thick lead wall or a thick concrete wall. Okay, it's absorbed, it's not repelled, it's absorbed by the thick lead or concrete walls. What happens if an electron, sorry, if a an atom produces an alpha particle? What happens if an electron, again an electron, an atom produces a alpha particle? Let's see, if I have an atom X, okay, and it has a mass number, okay, let's say a mass number of Z and an atomic number of A. If it produces an alpha particle, which is 4 and 2, then the byproduct, okay, the byproduct would be Y, for example. But what happens to the mass number? The mass number decreases by 4, so Z minus 4. And what happens to the atomic number? It decreases by 2, so it's A minus 2. That's if it produces an alpha particle. What happens if X produces a beta particle? So X, Z, and A. If it produces a beta particle, 0 and negative 1, the mass number remains the same. The mass number remains the same. But the atomic number actually increases by 1. The atomic number actually increases by 1. So in both cases, the atom produced from this radiation, from this decay, is a different atom. Atom produced is a different atom. Y is will always be different than it wouldn't be the same. Gamma, it could produce the same element. We don't talk about gamma that much, but if we have any chemical equations, beta or alpha, okay, then we have to balance out the equation. Okay, I know it's more of a chemistry question because you need to balance out the equation. Sometimes it can produce alpha and beta. Sometimes it produces alpha, beta, and a neutron, for example. So we just need to balance out the equation. You need to make sure that the mass number is equal and the proton numbers are equal. Okay, you need to add up the mass numbers. For example, you need to add z minus 4 plus 4. It would be equal to z. So you just add up all of the masses and all of the atomic numbers found, and you need to just make sure that the equation balances out. You can have several things that happen in one equation. Again, it doesn't always have to be one alpha or one beta. Sometimes you can produce an alpha and a beta in the same equation, which is okay. You just balance out the equation. Um, okay, Okay, so this is alpha, beta, and gamma. Quite quickly, if we move on to the, let's say, the decay, okay, half-life, which is the most important part of this of this lesson. Okay, the half-life. What happens during the half-life, or what is the half-life? Okay, sometimes he might ask me, what is half-life? It's the time taken. It's the time taken. Okay, it's the time taken for the amount of radiation or decay or whatever radiation produced by an element or by whatever. You don't need to say by. Okay, the amount of radiation produced to decrease to half the previous amount. To have the previous amount. So basically, if I said that uranium today is giving off 1000 counts per minute, okay, if it's giving off, after let's say 10 years, it's giving off only 500. After 10 years, it's only giving off 500. So basically, 10 years is the half life, meaning that in another 10 years, meaning after 20 years, the amount of radiation would be even it would be half. Half of what? Would it be zero? No, it would be half of 500. So it would be 250. Okay. So every 10 years, what happens to the what happens to the amount of radiation? It is decreased by, basically, you have it. You divide by two. So basically, half-life, whenever you have a question regarding the half-life or the decay or the time taken or, you'll always divide by two. You will always divide by two. Some people might say, can I divide by 2 to the power of something? You can do that. You can do that. It would be a bit more difficult. Okay, you need to be very good in math to do that. Okay, you need to be very good in math to do that. But basically, for my simple way, I usually divide by 2 for several times. 2, 3, 4 times, whatever amount of time needed or required in this question or in this equation. Okay, I'll give you some, or we can actually start solving questions regarding the half-life. Okay, instead of giving you these uh, yeah, examples, we can just solve questions with actual examples. Okay, half-life, and there's another point when we're talking about half-life. There is something called the background radiation. Something is called the background radiation. Background radiation. What is the background radiation? Background radiation is the radiation produced by almost everything around us. Almost everything around us can give off background radiation. It is random, okay? It is we say it's called the random background radiation, okay? Random background radiation, and it's spontaneous. It's random and spontaneous. What I mean by random and spontaneous? Random means that you cannot expect which atom will decay at what time. No, you have no idea. Spontaneous meaning that nothing around it would actually affect the amount of radiation given off by this by this element. So, for example, you have carbon, you have whatever. The trees around us are giving off background radiation. My mobile phone is giving off background radiation. There is background radiation coming from the space, which is we call it CMBR, cosmic microwave background radiation. You have back radiation from almost everything around us. Radon gas, we have radon gas around us, which gives off background radiation. It's not okay. It's not harmful. It's not harmful, but there is the background. It's random and spontaneous. You never know what is the exact amount of the background radiation. Sometimes we take an average. How do we take this average of the background radiation? Using something called the GM tube, which is basically a device which measures we have a GM tube, which is a device that measures the amount of radiation for the different substances around us. So if you have something, you have uranium, for example. Okay, this uranium is now giving off some radiation. It's decaying. This uranium is decaying. If I use the GM tube to measure the decay of this uranium, would it give me the reading of uranium on its own? No, it would not give me the reading of uranium on its own. You need to first you need to measure the background radiation in the lab. For example, if you're doing this experiment in the lab, then first of all you need to measure the background radiation of the lab. Okay, leave the GM tube for a while and take the average readings, and then you have the average background radiation. And then when you bring the uranium near to the GM tube, the reading would increase. The reading would definitely increase. So if let's say this is my GM tube, I know it's not drawn like this, but let's assume that this is the GM tube. Okay, let's assume that this is the GM tube. If you leave it on its own, you switch it on, it will give a reading. Let's say, for example, the reading on its own is 50. Okay, 50 counts per minute. What is 50 counts per minute? This is the random background radiation. So this is the background radiation, 50 counts per minute. Then when you bring the uranium, okay, so let's say that this is a uranium isotope. Okay, it's a uranium isotope. It's giving off radiation, alpha, beta, gamma radiation. So what happens to the reading on the GM tube? The reading will increase. It definitely will increase. So let's say, for example, that the reading is now 1,000 counts per minute. Is this purely the amount of radiation given off by the uranium? No. 950 of it is from the uranium, 50 of it is from the background radiation. And therefore, when the uranium starts to, or when the amount of radiation starts to decrease, when it starts to decrease with time, what happens? Okay, you will start to divide by two. You will start to divide by two. But if you have background radiation, I need you to memorize this. If you have background radiation, what should I memorize? Minus, okay, divide plus. Okay, minus, divide, and plus. What do I mean minus, divide, plus? First of all, you need to remove the background radiation, so it's 950, and then you divide by 2 for whatever amount of time. Okay, you need to divide by 2 once, twice, 3 times, whatever. Okay, and then if he asks you to find the reading on the background on the GM tube after a certain amount of time, then you need to add the background radiation again. If he only asks about the amount of radiation given off by the source, the amount of radiation given off by the uranium, then you don't need to add. Then you don't need to add the background radiation again. Why? Because he's asking only about the source. If he's asking about the reading on the GM tube, then you need to add the background radiation once again. Minus, divide, and plus. Okay, for this question, for the uranium giving off some alpha, beta, and gamma, GM tube will detect it. Does it actually tell me whether the amount of radiation given off is purely alpha, or purely beta, or purely gamma, or a mix of whatever? No, it doesn't. How can I figure out whether it's alpha, beta, or gamma using 3 very simple tests, or maybe 2 simple tests? First of all, you need to measure the radiation as it is. So now it's 1,000 counts per minute. You need to first of all add a sheet of paper, a thin sheet of paper. Why? Why should I? You first need to add this sheet of paper. Why? Because this paper will tell you whether there is alpha particles or not. If the reading decreases, significantly decreases, okay? If it decreases by 50 or 100 or whatever number, if it decreases by a significant amount, then you actually did have some alpha particles. If it didn't decrease, then you had no alpha particles. And then when you can add the aluminum, thick aluminum sheet. Okay, when you add this aluminum sheet, what happens if the number decreases? If the number decreases slightly, okay, or if it significantly, I mean, if it decreases significantly, then you had some beta particles. If it didn't decrease at all, then you didn't have any beta particles. If the number, okay, decreases to zero when you have the aluminum, if the number decreases to zero or decreases to the background radiation, if it decreases to zero or the background radiation, then if it decreases to zero or the background radiation, this means if it's zero, meaning that there was no gamma radiation, okay, if it's zero or background, then you had no gamma radiation. But if it decreases to, let's say, 200 or 250, then you still have gamma radiation. That's why I'm saying you need to only do two tests. You can actually do a third one, which is adding a thick lead wall. You can apply a thick lead wall and see whether it decreases to zero or not. Okay, you can do that. But I'm saying experiments or two tests are sufficient for this experiment. Two tests are sufficient for this experiment. Okay, and then moving on, um, we have three more things we need to say. First of all, if you have a graph, okay, you have a graph. A decay graph will always look something like this. Decay graph will always look something like this. Again with the pen. Okay, decay graph will always look something like this. From this graph, he will ask you to find the background, um, find the half-life, find the half-life. So on this side, on the y-axis, you'd have the counts per minute. You have the counts per minute. On the x-axis, you'll always have the time. How can I find the half-life? Basically, you take the first number and you divide by two. Okay, take the first number. Okay, whatever. For example, if this is 10,000, okay, you divide by 2, so 10,000 divided by 2 is 5,000. This is 5,000, and then you can find the time taken. Okay, so this is the time taken, or this is the half-life. With a slight tweak, if you had some background radiation, if you had some background radiation, what should you do? For example, if there was a background radiation of 30 counts per minute, okay, 30 counts per minute. Okay, this is the background radiation. And the initial reading, okay, the initial reading was 530. You cannot divide 530 divided by 2. That's it. No, you cannot do that. What should you do? Minus, divide, plus. Minus, okay, I told you, you need to memorize it. Minus, divide, and then plus. So minus 530 minus 30 is what is 500. Divided by 2, 500 divided by 2 is 250. And then you need to add the background radiation again, which is 280. So for example, if this is 280, you need to find the time taken of 280, and this would be the correct time. Okay, this is if you have background radiation and you need to find the half-life using a graph. And then there was an experiment conducted by Rutherford back in the, I guess, in the early 20th century. Okay, this experiment, what was it? It was the thin gold sheet. Okay, the thin gold sheet experiment, in which he started to throw some alpha particles. Okay, he had some alpha particles. Okay, being directed at the thin gold sheet. In this experiment, what did he figure out? He figured out that most of the alpha particles moved, okay, most of the alpha particles just passed undeflected. Most of the alpha particles passed through the gold sheet undeflected, okay? 99.9% of them, okay, passed undeflected. Meaning that most of the atom was empty. Most of the atom is empty. This is what we know now today. Back then, they didn't know it. Back then, they had no idea what the atom was made of. They didn't know that the atom had a nucleus or that there was an electron shell. They had no idea. Okay, he conducted this experiment and started to find out these realizations about the atom. Okay, so most of the atom was empty because 99.9% of the alpha particles, these are alpha particles, moved or passed undeflected. Some of them, okay, some of them passed and started to deflect with an angle. Some of them passed and started to deflect with an angle. Again, with the pen. I don't know what's wrong with the pen today. Okay, again, some of them passed and they were slightly deflected. Okay, they deflected upwards or downwards. He figured that these alpha particles were repelled. They were repelled. So he learned that there was a central thing. Okay, there was a central thing. Back then, they didn't know it was a nucleus. Okay, there was something in the center of this atom that repelled this alpha particle, meaning that the center of the atom was positively charged. Was positive. Okay, it was positively charged. He knew that the alpha particle was positively charged, and therefore, when the alpha particles were repelled, okay, he knew or he learned that the center of this atom was positively charged as well, which we know today because the center or the nucleus has the protons. Again, if I ask you, what is the charge on the nucleus? What is the charge on the nucleus? You have to tell me that the charge on the nucleus is positive whatever amount of protons in this nucleus. Positive whatever amount of protons in the nucleus. I'm not asking about the charge of the atom. A neutral atom would have a charge of zero, yes, but the charge of the nucleus is always positive. Okay, okay. So this is the second thing he learned, that the center of this atom was positive. The third thing was that some of the alpha particles were uh, deflected back with huge angles. Okay, some of the alpha particles deflected back with huge angles, meaning that this center, okay, the nucleus has all of the mass, basically all of the mass of the atom. Of the atom. So these were the three conclusions he came up with this or from this uh, experiment. Okay. Last but not least, we need to find the direction of the motion. Okay, of different particles or different decays, different radiations as they move through either electric fields or magnetic fields. Through the electric field, it's quite easy. Through the electric field, it's very easy. Why? Because we have a positive field. Okay, we have a positive plate, and then we have a negative plate. A- An alpha particle is positively charged. An alpha particle is always positively charged. So it would be attracted to the negative plate. Alpha particle would be attracted to a negative plate with a large deflection. We say it's quite a large deflection. This is an alpha particle. What about a beta particle? A beta particle would be strongly deflected. Okay, strong deflection. We say strong and weak deflections. A beta particle would be strongly deflected towards the positive plate. Okay, alpha particle would be weakly deflected towards the negative plate. Why? Because the alpha particle is quite heavy, so it takes time. It's quite heavy, so it takes time to move the alpha particle towards the negative plate. And then last but not least, the gamma particle, or it's not a particle actually, it's a ray. The gamma ray is undeflected. Okay, gamma rays are undeflected. Why? Because they have no charge. Alpha, beta, and gamma. So it's quite easy when we're talking about an electric field. The more difficult part would be if we talk about the magnetic field. A magnetic field. Okay, magnetic field. Magnetic fields, we would be using Fleming's left hand rule or Fleming's right hand rule, depending on what. We have if I'm asking about the alpha, Alpha would use the Fleming's left-hand rule. Fleming's left-hand rule. Okay, but the beta, okay, would use the Fleming's right-hand rule. Or you can use Fleming's left-hand rule and just say it's moving in the opposite direction. Okay, you can do that. Fleming's right-hand rule. Okay, you can either use right-hand rule or just say that it's Fleming's left-hand rule, but it moves in the opposite direction. How so? The index finger is the direction of the magnetic field. The middle finger, instead of saying it's the direction of the current, it's the direction of the motion of this particle of alpha or beta as it's moving through the magnetic field. And then the thumb is the direction of the force on this particle, either upwards, downwards, into the page, out of the page, whatever, in whichever direction. Okay. So, for example, if I have a magnetic field which is X, okay, X is a magnetic field into the page. X is a magnetic field into the page. This is probably more commonly used. Okay, magnetic field into the page. And then we have the alpha particle moving to the right. This is the alpha particle. In which direction will this alpha particle move? Using Fleming's left-hand rule, you have the magnetic field which is into the page, and then the middle finger which is moving to the right. Therefore, the thumb would be pointing upwards. So the alpha particle would deflect upwards. With a weak deflection, we say it's a weak deflection upwards. What about the beta? You can use Fleming's right-hand rule or just say that it would move in the opposite direction of the alpha. Basically, it would move downwards with a strong deflection. This is the beta particle, and then definitely the gamma radiation would move undeflected through the field. This is the gamma radiation. Okay, I guess it's not that difficult. Basically, you need to use Fleming's left-hand rule or Fleming's right-hand rule. Gamma is definitely undeflected. Okay. Um. Yeah. Let's move on. Let's solve a couple of questions. Let's solve a couple of questions regarding the atomic physics quite quickly. Hope we don't spend too much time on this. Okay, I know it's quite easy. So I guess it's page what? Hmm. I have too many questions on the atomic physics. Too many questions. Why? Because literally there's literally no tests. Okay, you'd never have a paper four or paper two test without atomic physics. Okay, it's important. It's crucial. Okay, okay. So here we go. Page 469. Okay, page 469. Hmm. Okay, yalla, let's go. For each application of radioactive isotopes, state and explain which type of radioactive emission is suitable and suggest an appropriate half-life for the isotope. Okay, for the isotope. Household smoke alarm. The household smoke alarm. The household actually has to use what type of radiation? It has to use the alpha particles. Has to use the alpha particles. Why? Why especially the alpha particles? Because they are highly ionizing. Because they are very highly ionizing. Okay, they can detect that there is smoke. Okay, they will give off. They will set the alarm. Half-life of the isotopes. I guess they were around 60 or 70 years, something like that. You have a range. I guess you have a range, but you can write down around 60 years. They have a very long half-life. That's why you don't need to change the smoke alarm very often. Every 60 years, you can change this smoke alarm. Measuring the thickness of aluminum strips. Aluminum, aluminum. I said you need a beta particle. Why? Why especially beta? Okay, beta can penetrate through very thin aluminum. Okay, but it cannot penetrate thick aluminum. Can penetrate thin, but cannot penetrate thick. So it depends on. Okay, depends on um, the thickness of the sheet. If it's very thick, beta wouldn't pass. If it's very thin, it would pass. Half-life, you can just write down any half-life for beta. Okay, literally, you can just write down any half-life. Okay, it doesn't matter. Okay, anyhow, let's say 2 years. Can I say 2 years? Yes, whatever number. Okay, not required to know the half-life of this. Um, I know more difficult questions because this is variant 3. Always variant 3 have very intricate questions. Lead 20882 has the highest nuclear number of stable isotopes of lead. Stable isotope. Explain why lead 214 is radioactive. What's the difference between 208 and 214? It's an isotope. It's the same element. Lead, صح? It's the same element. But it's a different isotope. It's a different isotope. Meaning, okay, meaning that as you increase the number of neutrons, what happens? As you increase the number of neutrons, what happens to the element? It becomes more unstable. Becomes more unstable. Okay, so while lead is radioactive, it has much more, okay, much more neutrons, and that's why it's unstable, so it starts to decay, and starts to decay to decrease the number of neutrons. Number of neutrons. You might say, what if it starts to decrease? What if it starts to give off beta radiation, beta particles? If it starts to give off beta particles, then the number of neutrons also decreases. Why? Because to produce a beta particle, you need to change a neutron to an electron and a proton. So technically, the mass number, yes, remains the same, but the mass number remains the same. But technically, what happens to the neutron number? It decreases by 1. So you decrease the neutron number by 1 and increase the proton number by 1. The mass number remains the same, but the number of neutrons decreases. State two different sources of background radiation. You have several sources of background radiation. You can say cosmic microwave background radiation. So you can say radon, as I said, radon gas. You can say the trees. You can say the rocks. You can say mobile phones, the food, whatever you have. Okay, so let's say cosmic rays. Let's say the rocks, buildings, you can say food, trees, whatever. Okay. Question. Previous page. State what the numbers 92 and 235 represent in this symbol. 92 is the number of protons. Number of protons. 235 is the mass number. Mass number, which is the protons plus neutrons. Protons plus neutrons. Uranium-235 is a fuel used in nuclear reactors. State the process by which the energy is released from uranium in a nuclear reactor. What type of process? Nuclear something. I know it's a nuclear. Nuclear what? Nuclear fission. Nuclear fission. In the sun, on any star, what happens is nuclear fusion. We fuse hydrogen atoms to produce helium atoms. Describe the mass and energy changes that take place during the process in a nuclear reactor. Mass and energy changes. What happens to a mass? Okay, so first of all, you have a uranium atom and a neutron. You increase the number of neutrons. Again, see, you increase the number of neutrons, you make this uranium unstable. When it's unstable, it starts to produce different elements. I guess this is xenon, and Sr is strontium, probably, I don't know. And then two neutrons. Describe the mass and energy changes that take place. What happens? You can say that this uranium nucleus is converted into two other elements. Two other elements. What about the energy changes? Is the energy absorbed or is it released? Is the energy absorbed or released? You have to say that it is released, usually as thermal energy. So the uranium, okay, uranium atom is changed to two different other atoms, okay, two different atoms with smaller masses, with smaller masses, and energy is released during the process, during the process, usually as, okay, as thermal energy, as thermal energy. Okay, describe how thermal energy from the nuclear reactions is used to generate electricity in power stations. Okay, this is an easy part. What happens to this thermal energy? It heats up. It heats up water. Okay, water boils. Okay, turns into steam. Turns into steam, and then as the steam moves, it has very high kinetic energy. Steam rotates what? The steam rotates a turbine, which again rotates a generator, rotates a turbine, which in turns, okay, which turns a generator, producing electrical energy. State one advantage and one disadvantage of using nuclear fuels as a power station. An advantage is, we can say, it's a reliable source, okay, or that it's a as a we don't need that much uranium to produce huge amounts of energy. Very small amounts of uranium can produce very high amounts of energy. It actually doesn't produce, okay, it doesn't produce air pollution. It doesn't produce any air pollution. The smoke you kind of think, okay, is being produced. It's not actually smoke. It's water vapor. Okay, this is not smoke being produced from these nuclear reactors. It's not smoke. It's water vapor, which is not harmful. Okay, so it's no air pollution. You can say no air pollution, no air pollution, or very small amounts of fuel is needed. Okay, small amount of fuel is needed. You can say no air pollution. What about a disadvantage? It's it's very expensive to build. It's non-renewable. Okay, it gives off nuclear waste. Okay, which is very dangerous. Okay, it's extremely dangerous. Okay, nuclear waste, which is very harmful. Okay, hmm. Yeah, let's solve one more question. One more question. Um, I guess this isn't a very difficult question. Okay. Hmm. Many household smoke alarms contain a sample of radioactive isotope americium. State how the composition of a nucleus of americium-241 differs from a nucleus of americium-242. 241. How is it different from 242? Americium-241 has one less neutron than americium-242. They have the same number of protons, okay? An atom of a different element of a nucleon number is 241. Different element, nucleon number 241. Two differences between the composition of this element and americium 241. Different element. It has the same mass number. So that it definitely has to have a different amount of protons and a different amount of neutrons. Different protons and different neutrons. Yes, they do have the same mass, but they have different protons and different neutrons in the nucleus. Okay, americium, I don't know. You don't know the proton number. And then you have neptunium, and alpha. We definitely know alpha, which is 4 and 2. 4 and 2. So can I find the proton number of americium? Yes, 2 plus 93 is 95. Can I find the mass number of the neptunium? Yes, 241 minus 4, which would be 237. 237. Hmm. One reason for using an isotope that emits alpha particles in a smoke detector is that alpha particles are more strongly ionizing than beta particles. Explain why alpha particles are more strongly ionizing. Why are they more strongly ionizing? Because they have more charge. They have more charge and they have more kinetic energy. Okay, they have more charge and more kinetic energy, meaning that they can easily ionize the other elements around them. Okay. The isotope of neptunium produced by americium-241 is also radioactive. The decay of the isotope of neptunium produces an isotope of protonium, which decays beta particles. Beta particles are more penetrating than alpha particles. The half-life of neptunium is longer than 2 million years. Using this information, explain the advantage of this long half-life for the use and safe of disposal of a household smoke alarm. When the americium decays, it produces proctanium, which has a very 2 million years. 2 million years. Is this or would this element be dangerous? Would it be dangerous? No, it wouldn't be dangerous. Why? Because in this case, there's no harm. There is no harm from the decay. Okay, when it decays too much, it produces too much radiation, meaning that this radiation could affect us. But since the half life is too long, then it wouldn't give off that much radiation. Okay, so you can say less activity, less decay over time. Okay, and this means that it's not that dangerous. Okay, less decay over time, meaning that it's dangerous, less dangerous or harmful to us humans. Hmm. Okay, that's enough for today, I guess.